In this lesson, we are going to look at the Hall effect. Now, the Hall effect is a voltage measurement, and it was discovered by Edwin Hall in 1879. And it is a very powerful experimental technique that is used even today by atomic and molecular physicists to classify materials, to measure things like the drift velocity. We're going to see how the Hall effect is used to measure the drift velocity and actually used to measure the number density of charge carriers in the materials as well. So when you want to classify a material, when you have some new substrates, some new materials that you've developed for a material scientist or an atomic and molecular physicist wants to classify a material, they will often take Hall effect measurements to see what the electrical properties of that material is. Well, how does the Hall effect work? The Hall effect actually involves a very simplistic setup. The Hall effect utilizes a voltage source, so for us, a battery, that is connected to the material. In this case, we're saying it's a metal plate. And we connect the positive terminal of the battery, solder a wire to one end, solder a wire to another end, and connect it back to the negative terminal of the battery. I have it drawn in a linear sense here, but we would actually have to connect it back to the negative terminal of the battery in actuality. And we are going to measure the voltage on the top of the plate relative to the bottom of the plate, as we have here and here. Now, let's first consider conventional current. So we're going to let the flow of current, conventional current, go to the right. That's positive charge carriers. We are going to utilize a magnetic field because the Hall effect always utilizes a magnetic field. So we have a north pole of a magnet here, the south pole of a magnet here, generating a B field straight into the paper, perpendicular to the plate. And now, when we very carefully do QV cross B, we get a thumb up. So we would have positive charge up here, leaving negative at the bottom. And if we put a multimeter measurement to measure the voltage between the top and the bottom, we would measure the voltage between those 2 points. Well, let's consider the electron flow, because when we have a battery connected to the plate, the actual flow of electrons, we know, is backwards against the conventional current. So now we have QV to the left. We still have B into the paper. So we have our north here and our south here. Now, when we carefully do QV cross B, it's thumb down, but it's electrons, so we reverse our thumb direction, thumb to the top. So now we would say we have negative at the top and positive at the bottom. And the first question we have is, which of these polarities is actually the correct polarity? So if we actually connected a battery to this metal plate and sent a current through the plate, which polarity would give us the correct polarity? Well, let's go on to the next page and see which of these polarities is actually the correct polarity. Okay, so it turns out that the Hall effect gave a definitive way for scientists to know that the electrons are actually negatively charged particles moving against the conventional current convention that Ben Franklin gave us with positive charge carriers, and that electron current is truly the correct current for the flow of charge in metals, and that electrons will be pulled to the top, and we will have a negative polarity at the top, a positive polarity at the bottom. And please make sure you add to your notes that you are not going to look conventional current for Hall effect, so put in there, do not use conventional current ever for Hall effect, and that you will always use electron current when you are ever asked about questions to determine Hall effect polarity. Okay, let's get on to the other really neat aspects of the Hall effect. The first really cool thing that Hall effect does is it allows us to mechanically measure the drift velocity of the electrons in that metal plate. And if we consider that if we put this plate on a table where we could mechanically, by mechanically I mean actually, literally, move the plate to the right. So if we could pull this plate to the right, so move the plate to the right with speed v drift, at that point you would have no relative motion between the Q's moving with speed v drift and B external, and the Hall voltage then collapses, goes to zero, and V drift is now mechanically measured. So really cool. We have a mechanical means of actually, literally measuring the drift velocity of the electrons in that metal. And the Hall effect gets even better because we don't have to actually use a mechanical measurement. We can use a crossed fields measurement to get the drift velocity. Well, the crossed fields measurement comes about because the Hall voltage actually has a Hall electric field. Voltage equals ed, where the D is the distance between the polarity on the top and bottom, basically the width of the plate. And what happens is when the Hall voltage reaches a maximum value, it maxes out. At that point, the pull of the electrons to the top, right, by QV cross B. So the pull of the electrons to the top and the Hall voltage electric field, which notice the electrons are going to want to be pulled down by the electric field, F equals QE. When those two equal each other, the Hall voltage has maxed out. The polarity will stop building. At that point, we have our crossed fields situation. We have the B field going perpendicularly into the plate, the electric field in the plate going straight up at 90 degrees to each other. We get that the drift velocity at that point equals electric field divided by B external, and of course we can know the electric field because we have our voltmeter to measure the voltage, and we can of course take a ruler and measure the distance D. So really cool. And it gets even better because remember, I equals QNav. We could put an ammeter in this circuit and measure the actual current value, so the amperage through the plate. We know the charge on the electron is 1.6 times 10 to the minus 19. Millikan gave us that, so we'll talk more about that and see how Robert Millikan gave us the 1.6 times 10 to the minus 19. The cross-section of the plate, of course, would be known. That could be measured. We just said we would know the drift velocity from the Hall effect itself. And again, voila, we have the only unknown is the number density of charge carriers. So the Hall effect also allows us to measure the number density of those conduction electrons is now a measurable quantity. So the Hall effect is very powerful, still used today, again, by mostly atomic and molecular physicists, electrical engineers, and material scientists who want to really understand the classifications or characteristics of different materials, metals, and their conductivities. So we have one more lesson in Chapter 30, and hopefully you have learned a lot about how magnetism affects the movement of charges.